Okay, so for unitary evolution, this is kind of straightforward to see, right? This corresponds to the single channel E, right? So that there aren't different outcomes. There's only a single E. There's, K is one. Um, and what does it do? Well, this is kind of straightforward, right? Because the E of rho, right, is going to be corresponding to unity, is going to be dagger, right? And uh, clearly, new dagger U is identity, right? Okay, so that was the first one. Then the next one is about an observable. So I'm going to remove this part. No. Okay. So what is the next thing? The next thing is as we look at observables. What do observables do? So suppose that O is in this form, lie pi I, sum over I, right? Um, then the sequence of channels EI is follows. So the sequence of channels EI is going to be defined as follows. The EI of rho is just going to be acting as pi I rho pi I, proportional. So you normalize it. Okay. So that's the statement, and then so it's easy to check. So clearly pi I dagger I equals uh, right. So they are Hermitian, right? So pi I dagger pi I just be pi I square, which equals pi I, right? And this is going to be at most identity, right? And why is that? Because this has eigenvalues 0, 1. Okay, so this will be at most 1. Um, and what about measurement operators? So measurement operators are, um, we're going to use the ones from the POVM, right? So measurement operators are given by an I dagger and I, right? And okay, so the channel VI overall is we're going to define it to be uh, proportional to the same, right? So NI and I dagger, and again NI dagger NI is at most identity because we know that the sum of these are positive operators that you're adding and the sum to identity, and these are all positive semi-definite. Okay, so if you remove some of them, this inequality is still true. Okay. This basically shows that the three kind of things, unitary evolutions, observables, and the general measurement operators that we looked at can be seen as special cases of channels. Okay. Um, okay. Now we're going to look at there is some intuition one can give about why this operator sum representation appears. The one way of thinking about it is to coarse grain the measurements. So suppose that you start with, so you suppose you had. Okay, so what am I doing here? Okay, so maybe I should write the story here is uh, uh, viewing this operator sum representation, basically motivating the operator sum representation. Okay, so motivating the operator sum representation. And how does that work? So the operator sum representation is going to say the following. Sorry, we already know what it says. Now what we're going to do is we're going to look at, so suppose we're going to look at the following example. So suppose that you have some measurement operators. Suppose your uh, measurement operators um, and ni dagger ni. Okay. Um, and then so this say this is situation. So let's say this is experiment one. So experiment one is you measure ni dagger. Okay. And experiment two is you have some sort of a faulty device that measures ni dagger ni, but cannot distinguish uh, but maps I say I1 and I2 to the same index, let's call it K. Okay. So what this means is that if you see outcome K, so in experiment two, if you see index K or outcome K, okay, the so how could you have seen outcome K, right? It would have been when you got, okay, so let's just do this. You see outcome K with probability space of ni1, so ni1 vector plus space of ni2 row ni2 vector, right? And the post measurement state would then become also a probabilistic mixture, right? So, with this probability, so let's call it P1 for now. Let's call this P2. Okay, would be so. Okay, so with probability. Okay, so what would the state be? So with probability P1, it would be the post measurement state here, which is ni1 row ni1 dex by P1 state plus, because that's the normalized state, right? And P2 by ni2 row ni2 dagger divided by P2, right? And so you get this. So yeah, so all I was trying to say was that you essentially get how the operator sum channel acts, right? So you get a combination of these measurement observing operators acting on the state row. So you can think of the operator sum representation as essentially arising from coarse graining measurements, the generalized measurements that we considered. Okay. But of course, this is not the full proof. For the full proof, I'll refer you to the book. Okay, so uh, that's all I wanted to say for motivating the operator sum representation. And now we're going to look at a nice characterization, or another characterization actually, which is very useful of this operator sum representation, or in fact an ECP-TP map, basically, which would be as follows. So I'm going to erase this. And let's remove the story part. Okay, so the other characterization, which would be helpful for us, is called the Stein spring. representation of channels. So theorem 58 is the sign string representation of channels. And what is this represent? Sorry, what is this representation? It says the following. It says for any channel E. Yeah. Okay. One maybe small thing I would like to mention is that from now on, we're going to assume that these E's, these maps, they satisfy. Yeah, maybe. Okay. So in this language, I want to say that it's actually equal to identity. Okay. And that's mostly without loss of generality because you can always, so instead of considering different outcomes, like different channels corresponding to different outcomes, you can just have one channel and store the outcome in another qubit. So then everything still works fine. Um, okay, so for now, all I'm going to say is that we're going to look at channels. From now on, we're going to look at channels for which this is one. Okay. So that trace preserving channels, not trace non-decreasing. Okay, so for trace preserving channels, which is so for any channels, I'll just write this time just to be clear. So trace preserving channels, say E from operators on X to operators on Y. Um, okay, there exists a Hilbert space Z of dimension product of dimensions X and Y opposed to the product of dimensional X dimensional Y. So this is one thing. The other thing is an isometry. An isometry A. What is an isometry? A dagger A is identity. Okay. Um, so this isometry goes from X to Y tensor Z. Okay. So you have an isometry such that one can express the channel here, so EX, as trace of Z. So trace out the Z space, X A that. Yeah. This is called the Stein-Spring dilation for the qubits. You can say you can put rho if you want for each density, or linear operators. Okay, so that's the theorem statement. And so what is nice about this is you don't have to necessarily worry about the sums. You can just look at uh, the isometry A. And the other nice thing here is that one can express the isometry as a unitary as well. So here is a claim. So I'll just draw the claim in pictures. Okay, so this is claim 59. You can look at it for details if you want. So what this is saying is that suppose you have an isometry array. Here's an isometry A. Okay, and so this is your rho. Okay, and suppose that your X is an n-qubit Hilbert space. Okay, suppose Y is an m-qubit bit space, and your Z would be n plus m qubit, right? Because the dimensions are getting multiplied. Okay. So so the input space here is n qubit, okay, and it produces say some channel phi, what we were writing as E. Okay, so let's write it. Be consistent. E of rho. Okay, this uses n qubits, and then the remaining qubits here are traced out. So you trace out. So A was going from x to y tensor z, right? So you removed m qubits. So the qubits that are left are n plus m qubits. Okay, this is what you're tracing out. Okay, so far I haven't said anything. I've just drawn the picture for what this operation is doing. But it turns out that this thing is exactly the same as having a unitary, okay, which is the same here. So this is again m qubits. This is again this is trace out. Trace this out. Okay. So similarly, you trace out that part here, and the initial state is this is rho, and the to be a unitary, you kind of have to match the number of qubits. So you had n qubits here and n plus 2m on that side. So these would be 2m qubits here. So you have the state 0 and set 2m acting on the unitary. Okay, the claim is that these two are equivalent. Right? So it's basically the same action. So instead of applying the isometry A, you can apply the unitary U with m qubits in the beginning, set to 0. Okay. Yeah, so that was all I wanted to say about channels. And now we look at quantum circuits.